Professor, you're on mute if you're speaking.
I sure am. Thank you. Sorry about that. I was just presenting earlier today and I had it all right. And so sorry about that. Okay, we'll get going. It's February 18th and this is Civil Engineering 481, Transportation Engineering. And we are going to be covering today, we're going to continue on with chapter 3, but we're moving into the horizontal curves portion or horizontal highway design portion of the chapter. As I mentioned to you before, I think it's a little backwards to start with vertical and then go to horizontal, but that's where your book goes, so that's the way we're doing it. So I'm going to spend time today talking about the horizontal curves and you know, we're going to go over a few problems on how to go about doing that. And you know, horizontal alignment has issues that you have to be aware of as far as sight distance. We'll talk about that today, and you know, minimum curve radius, things like super elevation. You know, the radius of the curve can affect how fast a vehicle can safely negotiate a curve, that sort of thing. So we'll be doing that. So anyway, welcome everybody back today. And I just want to remind everyone that by the end of class today, I need to be notified by you if you want to create your own group, because tonight I'm probably going to assign everybody in the class to a group randomly for those who didn't express a desire to be with certain people. And so this is your last reminder for that. Over the weekend, I will be sure to post the groups, you know, over the weekend, because again, our first group assignment is going to be on a week from today, on the 25th. So I want to get I want you to know who your groups are over the weekend, so you have all of them next week to touch base and that sort of thing. So anyway, that's just a reminder about that. So and I already posted, I think on Tuesday, I posted the homework, the horizontal curve homework. Let me see. Excuse me, I posted the vertical curve homework on Tuesday, and it's due on the 23rd. And on Tuesday, the 23rd, I will post the homework for the horizontal curve portion of the chapter. So that just gives you all the information there to get you up to date with where we are on the class. Any questions before I jump into today's material? Okay, then let me go ahead and get started. Let me put this here. Okay, so I'm sharing my whole screen today so that you can see. First of all, I actually increased the size of the cursor because I figured when I go over problems, it might be helpful when I'm trying to point something out in a problem to have a cursor that's just a little bit bigger so you can see it a little better. Hopefully that's helpful. It's helpful for me. I wear reading glasses, and even with the reading glasses, it's helpful for me to have a little bigger cursor, so you may notice that today. And then what I wanted to make sure I could see any chat questions that people have. And then over here, I've got, as I've done before, these are the equations that we had for chapter 3. These are all the vertical curve equations we went over in the last couple of classes here. Let me just adjust this a little bit. There we go. And now we are going to be covering horizontal curves, and so these are the equations we're going to be discussing today. So I have them here so that we can easily reference them as we're going through the slides. So, okay, so let's start talking about horizontal alignment. It starts on section 3.4 in your book, after the vertical curve section. So basically the horizontal curves are the alignment feature that connects two straight sections of highway, or what is often referred to as tangent sections of highway. I'm sure that's what you got in your surveying class. And so basically highways are a series of tangent and circular curve sections, and we'll talk about the issue of circular curves and so forth. That's all highways really are: tangents and curves, tangents and curves. And there's a few other things there in terms of all of the features that go into highways and stuff, but in terms of the basic horizontal alignment, like what you would call the layout or the map view of a highway, like you're up in the air in a helicopter and you're looking down, or an aerial view of the highway. It's a series of tangents and curves. And so the curves, what comes into play for curves is cornering capability. This gets back a little bit to chapter 2 and, the performance of vehicles. And vehicles perform, have limitations on how they will perform, and they're governed by, physical or physics governs how vehicles negotiate through the curves. Obviously, if you have a really tight curve, you can't go at, you can't take a really tight curve at 100 miles an hour. I mean, you just inherently know that. You can't do that. You need a flatter curve at higher speed. And, tight curves require lower speeds to negotiate them. That's just, common sense. And so the figure 312 in your book is in the next slide, which is, kind of a vehicle cornering slide. And again, it's one of these, diagrams that helps us understand the physical equations that are derived from it in order to be able to calculate the design parameters of the highway. And in this case, this is cornering. So you can see if a vehicle is traveling through a curve is very rarely perfectly flat, i.e. you see this angle here. See, the cursor helps, it's big. And the angle alpha here, even though this isn't like, this makes it look like it's 30 degrees or something, it's generally a more gentle angle than that. But still, vehicles that go through curves, this is what, this refers to kind of the super elevation of the road, because a vehicle can't, very rarely is alpha equal to 0 in any curve, other than maybe a true intersection where you're making a 90-degree turn and you're negotiating that turn at slow speeds anyway. But in terms of the alignment of a highway and an alignment that has a curve in it, there's always going to be some incline to the curve to deal with some of the forces that you see on the diagram here. And you can see what all of the definition of the terms there. This is the R sub V is the radius defined to the vehicle's traveled path. So let me go back here and see. R sub V right here is the radius of the curve, the horizontal curve, but it goes to the vehicle itself, where the vehicle is driving. R, just the radius of a curve, refers to the center line of the road. So if you have a 2-lane road, the center line of the road is basically right in between the 2 lanes. But R sub V would be, let's say the lanes are 12 feet wide, R sub V would be 6 feet less than that, because you're looking at the radius of the vehicle, the travel path of the vehicle, so to speak. And you'll see that as we start going through the problems, what the difference between R sub V and R. As I already mentioned, alpha is the angle of incline in degrees, but E is the number of vertical feet of rise per 100 feet of horizontal distance. It's basically the grade, you know, in vertical curves, when we were saying it's a 2% grade, well, here we're referring to a 2%, I'm sorry, let me go back, a 2%, for example, if you know, whatever angle corresponds to, you know, a 2-foot rise over a 100-foot run here, E, the super elevation is said to be 2% here, E. So that's the value of E. W is the weight of the vehicle in pounds. Then you also have the, you know, that the weight expressed both normal to the roadway and parallel to the roadway. You have side frictional forces or centripetal forces, the side frictional force here, F sub F, and then you have the centripetal force, F sub C, and the centripetal force acting parallel to the roadway surface, and the centripetal force acting normal to the roadway surface. Let me just go back, and so you can see all of these various forces that are acting on the vehicle as it's driving through at speed through a horizontal curve. Okay. So based on that, just like we've done in the previous courses or the previous classes, like for the derivation of the equations based on, you know, the physics of the traveling of the vehicle and so forth, basically you start out here with the weight parallel plus the frictional forces is equal to the centripetal force parallel to the road. And you do some substitution in there and you get this equation 332, which introduces a new coefficient, which is F sub S, which is the coefficient of side friction. Basically, when there's an angle to the roadway in the curve, there's going to be some side friction that holds that vehicle in place. And you'll see we'll discuss a little bit about how that can change, particularly in poor road conditions, like what I guess 90% of the country is experiencing right now, which is freezing weather. And so when ice is on the roadway, this coefficient of side friction becomes important to understand and how that can impact the performance of vehicles and the safety of negotiating the design of a highway. So, you know, you continue to go through the derivation where you divide both sides of that previous equation by W cosine alpha, and you get this equation 333. And then what you can do is you can make some conservative assumptions and ignore the normal component of centripetal force, which is relatively small. And ultimately, this equation boils down into equation 334. And notice I've got the highlighted equation here, 334. This is the first one. And I've got it up here in the list of equations. For some reason, my cursor changes to a funny symbol on a PDF file up here, but in any event. And so basically what it says is the radius to of the vehicle's pass, R sub V, this is how it's related to the speed of the vehicle and the side frictional, the coefficient of side friction, and the super elevation rate. So you can see that's how you can figure out. So this is the kind of equation you might know what the radius is, for example, and you might know what the speed is, and then they'll say what is a safe super elevation to use given a certain radius, given a certain speed, that kind of thing. So you'll see, and there are some tables that can help you with that as well. So as it says here, when you start talking about the minimum radius that you would use for a curve, you know, how do you decide how tight the curve or how general the curve should be for a given circumstance? So the selected value of the super elevation is critical because high rates of super elevation you can't just make it super steep. I mean, the steeper you make it, the faster the car can go generally, But the issue is that if you use too high a super elevation rate, maybe some of you have seen some of those test tracks they do for vehicles, experimental vehicles and stuff, like in Germany, that I think Mercedes-Benz has a test track where the super elevation is like, I mean, the banking on the curves is almost, you know, perpendicular to the ground. I mean, the car's basically hanging on the side, or it's like a roller coaster that's got, you know, that can put the roller coaster in that level. But if you do that on a road, what happens in cold climates, ice on the roadway, you have to think about the road in all conditions. And if a car is traveling at a high rate of speed in good weather, it'll negotiate the curve fine. But if it's going slowly in cold or freezing weather, and most vehicles do and should slow down during cold weather, then it can, if the super elevation is too high, the car can actually slide down the curve. So that's why you have to balance these things. And that's the coefficient of side friction, this F sub S, can come into play. So selecting a super elevation, E, and a design speed, V, which is the speed of the vehicle, and using a maximum side friction, you can get a minimum radius. And so table 3.5 in your book is important for understanding these concepts of you know, super elevation and side friction, et cetera. So table 3.5 gives the AASHTO guidelines for selecting, once again, AASHTO, American Association of State Highway Transportation Officials, guidelines for selecting values of E and F sub S. So you'll see in that table, if you go to that table in your book, you'll see that you can, you know, basically, if somebody says we're trying to achieve a design speed of 60 miles per hour, you can look up and see what are you know, appropriate values of E and F sub S. So let's talk about horizontal curves for a moment. There are a few options for curve types to connect tangent sections. You can pick simple circular curves. You can have reverse curves. You can have compound curves and spiral curves. And in this course, and when you deal with highway design, nearly all curves are simple circular curves. There are a few ramp designs where you might have a compound curve. A compound curve would be you have a single curve with multiple radius in it. And reversing curves is something that is generally kind of frowned upon in terms of designing curves, because if you think about it, if you take two curves and put them, if you connect them in reversing order without a tangent in between, it's really hard to flip the super elevation. You know, because you've got to, the curve has to be, if you reverse the curve, the super elevation has to be changed, and you don't have enough room to make that happen. That's something that you'll get into if you take civil engineering 482 highway engineering class. They get more into the details of how to design super elevation, but you can just imagine that. Now a spiral curve is different, and if you ever get involved in designing railroad, whether, and the rail could be heavy rail, it could be light rail like the trolley here in San Diego. Generally, rail, they have spiral curves, which is a kind of a parabolic, like when a tangent starts into a curve for rail, they start into a spiral curve, which is a parabolic curve, which is a little bit more gradual of a curve, and then it ties into a circular curve. It's almost a transition from a tangent section into a curved section of rail, because rail, you know, it has a lot more restrictions on its movement than vehicles do, or automobiles do, and so therefore they are used for rail. But this is we're focusing on highways here, so every project that we have, the curve will be a circular curve. So a circular curve has a single constant radius from the beginning to the end of it. And so we will go over the elements of the curve. This figure 313 is very useful for, this is the most basic horizontal curve sketch or figure that you can use, and it shows all of the various relationships here. You've got, again, this R is different than R sub V. This R is to the center line of a roadway, not necessarily to where the cars are traveling. This would be, for example, if this is a two-lane highway, one lane in each direction, this would be the center line of that highway is the R radius. Then the central angle is delta, and so if you split at the PI here where the two tangents meet each other, you've got delta over 2 on either side. The tangent length is from, well, let's start with the PC. The PC is and in some cases people call this the BC, beginning of the curve, but this is the point of curvature. You've got a tangent leading in here, and this is where the curve starts, and the PT is where the curve ends. The PI is where the two tangents intersect. And it just so happens, you can do your geometry to figure this out if you want, or your trigonometry, whatever, that the angle formed by the two tangents here is the same as the central angle here, delta. This angle here equals this angle here. You can prove it to yourself if you want to, but trust me, it's there. The tangent length runs from the PC to the PI, to the intersection of the two tangents, okay? And it's measured along that line, okay? But the length of the curve is measured along the curve itself. So this is really important, because what happens is, if this is, let's just say the PC is station 100, okay? If this is station 100, then if you want to know where the PI is, you just measure directly along the tangent to get the station of the PI. But you have to actually add, and then if you add the tangent length again over here, that will not give you the station of the PT. The station of the PT will be determined by the length of the curve, not by adding, running the stations up to the PI here and running the stations to the PI here. So it's a little bit, you'll see that in some of the problems, but it's important, because sometimes people, they'll say when it's you're given the station of the PC and you've got the information to calculate the tangent length, some people will just say, okay, they'll add the tangent length to get to the station of the PI, then they'll add the tangent length again to get to the station of the PT, and that's wrong. You've got to add the length of the curve to get the station of the PT. Just, you'll see that in some of the problems that we'll do. So I wanted to spend a little time on this diagram because it's the most important. And so these are all, I've already gone through all these things. The one thing I'll mention is that E and M are less important factors in this drawing. M comes into play later when we start talking about stopping site distance. So, but even that, it's not exactly here. So what I would tell you is that the most important, we went over the radius, the central angle, the PC, the PI, the PT, the tangent length, and the length of the curve. The middle ordinate and the external distance are less important factors that you need to understand. And that's why in these circular curve formulas that are all in your book, 35 through 39, I have highlighted 2 of them, and I put 2 of them over here in the little list of key equations, and that is this equation relating on how to calculate the tangent length and how to calculate the length of the horizontal curve itself. These are the 2 most important. We do kind of make a modification of this middle ordinate. I think they call it the middle ordinate. Yeah, the middle ordinate here. We have a modification of this equation here that we use for stopping site distance, which we'll get to in a moment. But these are the two most important ones for solving the problems that we'll be working with in this class. So now that we've given the basics of horizontal curves themselves, we want to talk about sight distance for horizontal curves because it's different than the sight distance for vertical curves that we've gone over previously. So the sight distance restrictions on horizontal curves when obstructions like buildings or rock outcroppings or retaining walls are present, as there'll be a figure that will show. Basically, if there's something that's on the inside of the horizontal curve, if you're driving through in a curve, there's something on the inside of that horizontal curve that approaches the edge of the roadway, that's going to obstruct your view to the other end of the curve, okay? So that's where sight distance comes into play for horizontal curves, is because, you know, basically there's something around the bend that you can't see because there's something inside the bend that's obstructing your view. So we'll get there and we'll show you that. So when an obstruction exists like that, it could be trees, you know, a big old tree that's in the way. You know, it might be something temporary. Somebody might park a big truck there, and that can be a concern. That's why you have red curbs and things, because you don't want big obstructions parked in a bad spot where you're going to obstruct somebody's stopping sight distance. So anyway, the stopping sight distance is measured along the horizontal curve from the center of the lane, of the traveled lane, the assumed location of the driver's eye. So when we start talking about that distance to an obstruction for stopping sight distance, we'll measure it from the middle of the lane as opposed to the center line of the highway. Once again, that's going to be important because that's really where the driver's eyes are at. And then as it says here in the following figure, there's a distance, m sub s, which is the middle ordinate of a curve that has an arc length equal to the stopping sight distance. Basically, it's the you know, well, you'll see it in the thing. You must have a clear view so that the line of sight, so that you have sufficient stopping sight distance for the vehicle. Remember, we did this for the vertical curves, let's say a crest curve where you couldn't see on the other side of the hill. And so depending on how severe the curve was, it had an impact on how you designed your vertical curves. It's the same thing for the same concept for horizontal curves, but it's calculated differently, and you'll see. So this is what we're talking about here, a sight obstruction. This is a horizontal curve. You're going along, there's a tangent coming out this way, and there's a tangent coming out this way, and you're going along the curve, but there's some major obstruction here, and this could be anything that, you know, like we said, trees, a building, you know, there could be a retaining wall here trying to keep the slope back, or it could be just the slope itself. And so you measure this m sub s is the distance from the middle of the inside lane where the driver, obviously that's the most critical part, because if somebody's going in the opposite direction over here on the other side of the roadway, they have more, you know, they have more distance, they can see more than somebody on the inside lane. And so this sets up a distance, a stopping sight distance here. And so you have, here's that R sub V again, because it's different than the R, which goes to the center line of the roadway. So R sub V goes here, and then you've got this offset distance, M sub S here. And then you have a central angle that corresponds to this, you know, smaller side obstruction alignment here. If there's no obstruction whatsoever, you just go by the, you know, the previous, you know, sketch regarding how to deal with designing your horizontal curve. But if you've got an obstruction, you got to take this into account. So basically, in order to calculate the stopping sight distance, we have some equations. So I'll just skip to the actual equation slide here. What you do is you look at the stopping sight distance and relate it to this delta sub S that was in the previous slide, and you can calculate delta sub S is related to the stopping sight distance. This is all just, basically, if you look at you can derive it directly from this figure 314. But then if you substitute that into the middle ordinate of a simple horizontal curve, equation 338, you get this equation here, which is, it's a variation of the one that I pointed out before, which is equation 342. And you can see I've highlighted it because this is the equation that we'll use to be able to calculate that minimum distance you need from an obstruction in order to achieve a certain sight distance. And it's related to the R sub V, and it's related to the stopping sight distance that you need in order to be able to calculate it. And you can also rearrange the terms of this equation in order to, let's say, there's the obstruction is given, you know what it is, you can test it against various curves and so forth, and you can then calculate what is the minimum stopping sight distance that you need in order to be able to, given the distance of the object. So these two are the equations. I've got them both listed over here in the list of key equations. So that's the material in the horizontal curve portion of chapter 3. And with all that, we can now apply these concepts, and in particular, all these equations over here, the horizontal curve equations, to be able to solve some design problems. So the first one I wanted to go over is example 314. And this is just a problem, a very simple problem on super elevation for horizontal curves. It kind of deals with this first equation, 3.34 here. So the problem says a roadway is being designed for a speed of 70 miles an hour. At a particular horizontal curve, it's known that the super elevation is 8%. They already know the super elevation, and the coefficient of side friction is 0.10. So determine the minimum radius of curve measured to the traveled path, measured to the traveled path that will provide for safe vehicle operation. So here's the key: determine the minimum radius of curve measured to the traveled path, which basically means R sub V, If they said determine the minimum radius of curve without saying this, then you'd be looking for the radius R, not R sub V, but they're specifically asking you for that. So you take equation 334 over here, which is the R sub V equals the speed squared divided by the acceleration due to gravity, G, multiplied by the coefficient of side friction plus the super elevation rate divided by 100. So basically you put in here 70 miles per hour. And again, you want to, because G is in feet, you want to convert that, our trusty 1.467 conversion factor to get 70 miles an hour into feet per second. You put that in and square it, and 32.2 times your 0.10, which is a given, and 0.08. And so because that's the super elevation rate of 8 divided by 100, and you end up with 1819.40 feet. So this value is this is the minimum radius. So that what this says, we'll go over what it says here, because any radii that's smaller than 819 will generate centripetal forces higher than those that can be safely supported by the super elevation and the side frictional force. So this would be the minimum radius. If you found out, or if somebody was proposing a 1,500 foot radius there, that would not meet the standards, given that you are looking at an 8% super elevation rate. And this, when they say 8% super elevation rate, that may be governed by the conditions. For example, on a 2-lane rural highway in areas that routinely get snow and ice. I believe that 8% is the maximum super elevation you can use. It might even be 6%. I can't remember off the top of my head, but you can't go to like a 10 or a 12% super elevation rate when you've got in an area where you routinely get freeze, icy conditions, because as we said before, a vehicle slowly negotiating a curve like that could actually slip down. That's too steep, and the wheels could actually slide on that. Okay, I got a question regarding the rounding, because somebody did this calculation. I'll admit I haven't run this through my own calculator, but somebody got something, about 18 point, closer to 18.6. And rounding is something that I'm not too concerned about. The issue is, for me, for example, if your answer is close, but you got it because you used R instead of R sub V, which doesn't make a huge difference in the answers, because these radiuses could be like, we have a problem we're going to go over where the radius, the R is 12, the R sub V is 1200, and the R is 1205. Okay, that's not going to make a huge difference, but it is important in knowing how to solve the problem. So I'm looking to make sure that you've set the problem up correctly, that all of the figures here, that rounding could be in 32.2. G is, you can get a more accurate or a more precise, I shouldn't say accurate, a more precise value for G than 32.2. For example, that might be the reason. 1.467 as the conversion factor for miles per hour to feet per second, that could be in there. So the answer is, I'm not too concerned about rounding as long as it's reasonable and within reason, and as long as you set the problem up properly. That's more important to me than exactly on the rounding. Okay, so that's a pretty straightforward problem that just gets to this first concept of super elevation and side friction, et cetera. Any questions on that one before I move on to the next one? Okay, let's go to the next problem. Okay, here's another problem and I will tell you, for horizontal curves, in my mind, doing sketches for vertical curves is probably a little bit more important, but I think it's important for both. And so what I did here for example 315 is I did my own sketch. Again, not pretty, but what did I do is I put into the sketch what I know and what I don't know, or what I know and what I'm being asked to figure out. Okay, so it says here, a horizontal curve is designed with a 2,000 foot radius. Okay, so that means that the 2,000 foot is R, not R sub V. They said it's a horizontal curve with they just mentioned radius. They don't talk about that to the driver's eye, etc. Okay, the curve has a tangent length of 400 feet, and the PI, which is where the two tangents intersect, is at station 103 plus 00. Determine the stationing of the PT. And I love this problem because it really gets into this issue of tangent versus curve length. Okay, so you're going to use equations 336 and 339 to solve this problem, which are the next two equations I have on our list over here. Okay, so here's my sketch. I don't know what the PC is. PC equals 0. That's what this shows here. Maybe you can't see that very well, but that's my writing. Okay, then the tangent length is 400. Now remember, the tangent length on this side, because this is a circular curve, the tangent length on this side equals the tangent length on this side. They're the same, okay? So you've got a tangent length of 400 feet. You do know that. You do know the station of the PI, and the station of the PI runs along the tangent here, 103 plus 00. You don't know the length of the curve. You don't know the PT. As a matter of fact, that's what they're asking for, is the station of the PT. And you do know that the radius, I marked it here along, the radius is 2,000 feet. And you don't know what the central angle is. They didn't give you that, okay? So what can you do? Well, if you look at these two equations here, which is the one that you can use to solve for something? You know what T is, and you know what R is. So therefore, there's only one unknown in this equation. So that's a good one to start with. You put in 400 feet for the tangent length, which was a given. You put in 2,000 feet for the radius, which was a given. And the only unknown is delta. So you crank that out and you find delta is 22.62. Now, let's look at equation, the next equation, 339. We've got, L equals pi divided by 180 times R times delta. Well, look, you know everything there, right? Pi and 180 are givens. R is 2,000, and you just calculated delta, 22.62. So you just put in those values here, and you calculate the length, which is 789.58 feet. Okay, now maybe if somebody cranks that out in their calculator, they'll get something a little different. Look, and they used a lot of times people just use 3.14 for pi, and they use 3.1416, whatever. In most calculators have pi in them, so you can use that. So in any event, we'll just say it's 789.58. So now the issue here, to get to the PT, a lot of people will just say, well, look, the PI is 103 plus 00. The tangent length from here to here is 400 feet. So isn't the PT 107 plus 00? And the answer to that question is no, it's not. Because what you have to do is you have to start at the PC and then add L to it to get to the PT. So but you don't know what the PC is. So how do you figure out the PC? Well, this is where you can use the tangent length, right? The 103 plus 00 minus 400 feet will get you the station of the PC. So that's 103 minus 4 is basically 99 plus 00 is the station of the PC. Now what you do is you take the station of the PC, you add the length, which you just calculated here, 789.58 to the 99 plus 00, and you end up with the station of the PT is 106 plus 89.58. That's quite a bit different than if you had just added the 400 feet to 103 and you had called it 107. That's not rounding. That would be incorrect if you had done it that way. Okay, so it's important to this is a really good problem, because basically they give you what is all this information, and then you have to back up and figure out what the PC is, and then add the length of the curve to it to get to the PT. Okay, any questions on that problem? That's some of the most basic, the basic requirements of a horizontal curve. Okay, what problem do I have next here? I like example problem 317 in your book because it's both vertical and horizontal curves together. So it's kind of, I like that we're dealing with both issues here. So 317, hold on a second. Give me a second here. I think I left off. Yeah, I left off the description of the, and I only copied the solution here. So I'll just read to you basically the description of the problem. I'll read to you, but it's basically all here in the two sketches, which were in the book, but I transferred them here to the slide. So they provide two sketches, a sketch of the horizontal alignment and a sketch of the vertical alignment. And I'll just note that they list the horizontal alignment first in the problem, or they show the figure first. So anyway, the description is a two-lane, you can go to example 317 in your book, but a two-lane highway two 12-foot lanes, which is what they represent right here, up here on the horizontal thing, has a posted speed limit of 50 miles per hour, okay? And on one section, and it has both horizontal and vertical curves as shown in these figures here, these two figures here. A recent daytime crash where a driver was traveling eastbound and striking a stationary roadway object resulted in a fatality and a lawsuit alleging that the 50-mile-an-hour posted speed limit is an unsafe speed for the curves in question and was a major cause of the crash. Evaluate and comment on the roadway design. Now, this is not unrealistic at all. That when there's accidents, the design of the highway can be called in to question in this case. Let's go ahead and get started. So basically, we have to look at sight distance issues for both the vertical and the horizontal alignment. And so what we'll do is they begin with an assessment of the horizontal alignment in the problem. And as they mentioned, there's two concerns: the adequacy of the curve radius and the super elevation, and the adequacy of the sight distance on the inside lane. So you have to check the super elevation and the radius of the curve, and you have to check. They show you that there is there's a side obstruction 18 feet from the edge of the traveled lane here. That's where it's measured to, not to the middle of the lane, but to the edge of the traveled lane. So you're going to have to check that. So for the curve radius, you've got you can figure out the length of the curve because they gave you both the PC and the PT here, 32 plus 75 and 16. So you just subtract one from the other and you end up with a length of curve of 1,675 feet. So that's part of what's given. Now you can use the equation 339, this equation here, and you can rearrange the terms to solve for the radius of the curve. You don't know the radius of the curve, but you know the length. They gave you the delta angle, and so you put all of those figures in. 180 divided by pi times 80 times the 1675, which you just calculated, and you end up with a radius of 1199.63. Just a tad under 1,200 feet is the radius of the curve. So if you use the posted speed limit of 50 miles an hour and you use 8% super elevation rate, which is given, and then you can use equation 334, and you can the only factor in that equation that you don't know is the coefficient of side friction, right? Because you've got the V is 50. G is G, and then E is the super elevation, which is 8. You know that, and R sub V is going to be, remember, the R that you calculated here, 1199.63, is to the center line of the roadway. So, and it was a two-lane highway with 12-foot lanes. So you need to subtract 6 feet from that to get your R sub V. 1199 minus 6 gives you the 1193.63. You put all that in, and you end up with 0.06 for your coefficient of side friction. And so you go back to table 3.5. The maximum side friction for 50 miles an hour is 0.14. Since the 060 does not exceed 0.14, the radius and super elevation are sufficient for the 50-mile-an-hour design speed, okay? So that part of it, the super elevation and the radius of the curve, is okay for 50 miles an hour. So if somebody's challenging whether 50 miles an hour is safe, at least from that aspect, you're good to go. Now you need to check the sight distance. And this is where equations 342 and 343, one or the other, come into play. So on this one, you've got what they use is equation 343 here. And what you've got everything you need to be able to solve this problem for the stopping sight distance, which is pi r sub v is given up here at 1193. And you've got 90 cosine, arc cosine r sub v. Then you've got this m, the distance m is 18 feet, but then you have to add half the lane width to that. That's 18 feet to the edge of the lane. So you add half a lane width to get to the actual driver's eye. And so that's 24 feet. You put that in there. That's everything you need to be able to solve that equation. You end up with a stopping sight distance for the horizontal curve and the sight obstruction of 479.5 feet. Now you go to table 3.1, the very first table in the chapter that relates stopping sight distance and speed. And so they say the required stopping sight distance at 50 miles an hour is 425 feet. So the fact that you've got just under 480 feet of stopping sight distance, that is sufficient, okay? So from a horizontal, from the design that you have here for the horizontal curve, you're good to go. It's adequate for 50 miles an hour. Now you need to turn to the vertical curve and make sure that it meets the stopping sight distance requirement, okay? So if you go to the Sag vertical curve, once again, they give you these two stations so you can figure out the length of the curve, 18 plus 80 minus 14. That means the length of the curve is 480. You can then use equation 310. This is going back to the part of the course that we were covering earlier on vertical curves, but the K equals L divided by A. You've got both grades, -2 and +4. So that means A is 6. You know, you calculated the length. So the K value is 80. So this is a Sag vertical curve. So you go to table 3.3 and it indicates a K value of 96, okay, for 50 miles an hour. So the K value of 80 is less than 96. So therefore, you would say that the curve is inadequate for 50 mile an hour design speed. But here's where this is a little bit of a trick problem. And I didn't copy it on the slide here, but at the top, it does talk about a recent daytime crash. They said the crash happened in the daytime, okay? So it says here, however, because the crash occurred in daylight and sight distances on Sag vertical curves are governed by nighttime conditions, this design did not contribute to the crash. So it's a little bit of a trick problem there, but it's to test your memory that really it's only nighttime conditions where sight distance on Sag curves matter. However, I would say this, it's probably not good to have it posted out there at 50 miles an hour if the design speed for this Sag curve doesn't meet that. And so that suggests that the curve the design is inadequate for any vehicles driving at night. And a lot of it, I assume the road's not closed at night, so it's still an issue. But in any event, I like this problem because it gives you both aspects of highway design, both horizontal and vertical, in order to be able, and it reminds you that there are multiple ways to check for stopping sight distance on a given stretch of highway. Okay, any questions on that one? Okay, got a few minutes left, and based on that, I think what I want to do is I've got one of your practice problems lined up here. It's practice problem 3.3, and this is a horizontal curve problem with design speed and sight distance. And so once again, I did this one, I have the actual problem portion, I copied that. So, but I also did another, I don't know why I'm getting that little hourglass figure. I don't know what that's, oh, I know why. I think I know why. I know why I don't. That hourglass is showing up because my my plug for my computer was just hanging on there. It had come out inadvertently and I didn't see it, so it was warning me that I was running out of juice. So that's good. That was great. So I'll be fine for the rest of the class here. Anyway, here's the sketch that I did, a horizontal curve. This is a 2-lane highway with 11-foot lanes, has a central angle of 33 degrees. So you can see I put in the 33 degrees here, and is designed for 60 miles per hour. So I put the design speed, you can barely read it here, but it's 60 miles per hour here. 8%, I put the super elevation equals 8% up here. If the PI station is at 300, so I marked it out, the PI where the two tangents meet is at 300. What is the station of the PT, okay, the ending station, and how many feet have to be cleared from the inside lane's shoulder edge to provide adequate stopping sight distance? And that's as far as I'm going to go in this problem. The second part of the problem where they talk about normal and component of the centripetal force, I don't think that's as important. I'm just going to stop right here. I want you to, I want to go through and calculate the station of the PT and talk about the clearance to the object, and basically solve for M sub S. Here is what you're trying to do. So the first thing you have to do is figure out what R is. Let me see okay. Basically what you have to do is you go to the radius for the R sub V for a 60-mile-an-hour design speed and a super elevation of 8% can be, you can get that from table 3.5. That's the first thing you need to do. And when you do that, you get R sub V. What I'll do is I'll go ahead and click through here. When you go to table 3.5, you'll see that R sub V is actually 1200.00. It's actually at 1200 feet. So what you need to do is you need to add a half a lane width to that in order to turn R sub V into R. And there's a couple of typos here in this problem in your book. This should just say lane width. It looks like half lane minus width. It's, I think, I don't know, maybe they tried to hyphenate lane width instead of just writing it as one word. So you take 1/2 times the lane width, which they said the lanes are 11 foot. So that's 5.5. And then it shows a multiplication sign here and it should be a plus. So 5.5 plus 1200 equals 1205.5, which is the value of R, okay? So R sub V is 1200, R is 1205.5 because you're adding half a lane width to it. So that's the difference between R and R sub V. So now with R known and, you know, delta is a given, you can now go to equation 339, which is the equation here, and figure out what the length of the curve is. So when you do that, you put in R, not R sub V of 1200, but R, which is 1205.5, and you multiply it by the delta, which is 33, which is a given, and you end up with 694.19. Now, if somebody does that calculation in their, I did that calculation earlier today, and I got something a little bit different than this figure, I think. I think this is the one where my rounding was a little bit different, but we'll go with the figure that they have here. It's not off by much, it's just a small amount. So now that you've got the length of the curve, okay, You can also use 336 and calculate the tangent of the curve, because what do you need for the tangent? You need R and delta. You've got both of those. So if you do that, you use R of 1205.5, the delta of 33, and you put that in and you get a tangent length of 357.08. So you've got L, which is 694.19, and you've got T, which is 357.08. So now it's just like the earlier problem we worked. Now that you know the length and you know the tangent, you start with the station of the PI, which was given, which was 300 here, and then you subtract from it the tangent length, and that'll give you the station of the PC here. So that if you do that arithmetic, you get 296 plus 42.92. And then to get the station of the PT, you add the length of the curve to the station of the PC. So on this calculation here, you add the length or the station of the PC, which you've just calculated, and you add the length, which you calculated up here, and you end up with 303 plus 37.01. So again, you have to, they gave you the station of the PI, you had to figure out both L and T, so you could back it up and then add L to it to get to the station of the PT. So now what remains in this problem is to determine how many feet have to be cleared from the inside lane's shoulder edge to provide adequate stopping sight distance, okay? So here you can use equation 342, which is the M sub S equation, right? So what do you need for that equation? You need R sub V, which you have. You need the stopping sight distance, which we're going to get, okay? So basically you go from, table 3.1, the very first table in the chapter, when you want to know what the stopping sight distance is for a design speed of 60 miles an hour, it's 570 feet. So now you have everything you need. You've got R sub V, and you've got stopping sight distance for the given speed of 60 miles per hour. So you put that into the equation, equation 3.42, and you put remember, this is R sub V, so it goes to 1200, not 1205.5, but 1200, and then you put 570 here, which you got from table 3.1, and 1200 under here, and you end up with 33.7 feet. That's what MS equals to. But remember, MS is the distance from the obstruction to the middle of the lane, okay? Where the driver's eye is. And what it says is it's asking how many feet have to be cleared from the inside lane's lane shoulder edge to provide adequate stopping sight distance. So that means what you have to do is you have to take that MS value of 33.7 that you just calculated and subtract a half a lane width from it, which is what they do on this last calculation here. So you take the 33.7 and you subtract half of 11 divided by 2, or 5.5, and you end up with 28.2 feet. And even though it's important to understand that the obstruction is measured from the driver's eye, when you're actually building the road, what can be important is sometimes they're asking for what is the clearance from the edge of the roadway, just in terms of building the road out there. So that's why they ask it that way in this problem. But it's important to understand what exactly is being asked for when you calculate these problems. So anyway, I think that that's the last problem I have to go over. And so basically, if you look at the list of equations that we have over here, there's this one that's focused on the coefficient of side friction and super elevation. Then you've got these two very basic circular curve equations for solving for the tangent and the length of the curve. And then you have these equations that relate the offset distance and the stopping sight distance for horizontal curves there. So hopefully this covers all of the issues, not hopefully, it does cover all of the material that you'll need to solve the horizontal curve problems in the homework that I'll be assigning at our class next Tuesday. So any other questions that any of you have on the material here? What I'm going to be doing on Tuesday is I'm going to do a little bit of review on chapter 3, and then I'm going to go through a set of highway design plans, or a couple of different sets of highway design plans. And I'm going to step you through them so you understand what they look like and how things like, you know, vertical curves, horizontal curves, you know, sight distance calculations and super elevation and so forth all kind of come together in a set of plans to actually build. I think the plans that I have are probably a major reconstruction of an existing highway. Frankly, there's very few brand new roads that are built these days, particularly major roads. It's mostly most of the work that's done on highways these days is modifying or expanding or making major renovations to existing roads rather than building brand new ones, or what they oftentimes call greenfield projects, building a road to a, you know, in a brand new. In San Diego County, for example, there are no new freeways, brand new freeways that are planned to be built anywhere, but there are plans to make major renovations to them. I mean, if you drive up Interstate 5 north of, you know, north of Solana Beach, between Solana Beach and Oceanside, you can see right now there's a lot of work going on I-5 right now, but that's all work on an existing freeway that's been there since the late 1960s. So that freeway's basically 60 years old, so it's getting a major update. Any other questions that any of you have? Otherwise, I would, let me stop sharing here. I would, you know, wish you all a great weekend coming up, and I think you have everything you need to be able to do the vertical curve homework. Chapter 3 is the only chapter where I actually have 2 different homework assignments, because I think there's enough material, in the material for vertical and horizontal is important to do independent of each other. So, but I think you should find the problems pretty straightforward based on the material we've covered in class. So any questions before we break up for this week and we get back together on Tuesday, the 23rd of February?
Yes, I have a question, Professor. I think it's pretty trivial, but I don't know why I'm struggling with it to understand. In the problem that we just worked on, the practice problem 3.3.
Yes.
Here, I'll use your slides instead of my book. So the 1, 2, 3, the third equation from the bottom where we plug numbers in, where it's 296 plus 42.92 plus this. How did we get that to equate the 303 plus 3701?
Oh, okay. Yeah, it's probably one of those answers is in station and the other answer is in feet. You could turn.
Oh, I see.
That's why. So you could, you know, it's just that when we calculated L up here, can you see my screen now?
Yes.
What I'm pointing to? Yeah. L here, L was in feet, but you could just as easily write it as 6 plus 94.19.
I see.
Yeah.
Okay.
And so, yeah,
All
so
right.
I mixed a station with just a length. And you can do it either way. You know, it probably is a good idea to keep them separate. It's just that when you get to a station of like 296, then the number looks giant, right? It's like 29,642.92. So it looks, you know, anyway. But yeah, that's what that's about.
Okay, perfect. That answers my question. Thank you.
Yeah, no problem. Okay, put that back off. Any other questions? Okay, everybody, have a really great weekend. I know I tell you to have a great weekend when maybe some of you have Friday classes. You know, so if you have Friday classes, obviously it's not really the weekend yet. But anyway, you know, I have a son who lives in Dubai. As many of you may know, the weekend there starts on Thursday is the last day of the week, or the weekend is Friday, Saturday, and the work week is Sunday through Thursday. So for him, it's the weekend, but for you guys, maybe not. Maybe you've got classes tomorrow, but if you have classes, good luck, and tomorrow, and I will see you all on Tuesday. Thanks,
All right,
everybody.
thank you.
Thank you.